Okay, hello and welcome. Welcome to day 10. The general idea for today is the cathode ray tube, which doesn't really tell me much. I'm not sure about you. The gist of it is we're observing this kind of input. So we either have no operation, which is very simple but takes one CPU cycle. Addx command, apart from just taking 2 CPU cycles, also adds a value to the X register. We will observe X register in particular moments, in the 20th cycle, and then 16th and 100th, and so on. Signal strength will be important for us. It is actually a multiplication of the X register and also the cycle number. The sum of the signal strength is 13,140. Let's see details in code. As usual, we have the input to our puzzle. It's a long scroll actually. Throughout the task we are actually only interested in X register value. This test focuses on building a list of that X register values. Last test covers reading the input and also observing the signal strength throughout the whole 220 cycles. To cover possible instruction types, we've got the type that is called instruction. We also have a type that I would call a helper one, just to underline whether it was no OP or add in general. The line either is no OP or is actually an add X. To build the cycle output, we do the following. First we create the dictionary that will tell us how many cycles the type of our instruction will take. That's why in here we've got add rather than addx, because addx needs a value. Let's read it from the end. First, we know the initial value of register X is 1. We also know that the shortest instruction takes 1 cycle, so we are sure that this second cycle will always be still 1. Then we cover all other cycles after the second one. To do that, we go throughout the instructions with our trusted map fault. If the instruction is no OP, we will add actually only one time the value of the accumulator. If however we are running instruction addx, we will create the first list of accumulators and then add increased accumulator on top of that. Since the actual length of no OP and add are constant, we could actually do it a little bit easier. In practice, this version of the match instruction would do exactly the same. For no OP, we would return the list that consists of the accumulator and also return the not changed accumulator. For addx, we would return the list of 2 values, the first one being the accumulator, the previous accumulator, the second one being the accumulator plus X, and without the change we would also return the new increased accumulator. I would say this version is actually much more readable. It's a little bit less flexible, however. All in all, I think I'll stay with the new version. And with that, we no longer need no OP and add instruction type. Alright, let's get back to build cycle output. In the end, we've got the list of lists of integer, so we need to flatten it out with collect ID. To be sure nothing really changed in terms of the functionality, we can take a look at the tests once again. And as you can see with the icons, Rider already mentions to us that those 2 tests needs to be run once more. I don't remember fully, but I think actually even the tests will have to change. Let's see. No, turns out I didn't use the instruction type within the tests, so the tests are still fine. Great. Let's move on to the full solution. To start, we lay the groundwork. We read the instructions, we calculate the X registry throughout all of the cycles, And now we start with cycle indices. What's in it, you ask? It's those cycles that we are actually caring about and want to calculate for. You specify the first index, the last index, and the step in between. As you can see, the cycles that we are actually interested in starts with number 20 and increase by 40 each time. That's why we've got 40 in the middle. We use that cycle indices as an input for our list map. Now what we calculate is the signal strength, which is the X registry value multiplied by the number of the cycle. Actually, using X in here is counterintuitive. Yeah, I like this better. And as always, let's see it in action. Here we go. And now part 2. Part 2 will be difficult to explain. Turns out that X register was actually correlated to the CRT display. If you have no idea what CRT is, you probably are a bit too young, but I remember those old-time PC monitors, which were not only massive in the end, but they were also curved, but exactly the opposite way as we have the curved monitors today. So the curved monitors today wrap around like this, right? But the CRT wrapped around like this. Old times. How CRT works in this particular example is that we are scanning throughout CRT like each and every line. Even more, we are creating a sprite. This is a sprite for the first cycle of the processor. The sprite always considers 3 pixels and they are placed as the X registry is showing. For the very first cycle, the X register value is 1, therefore the sprite begins at 1. Bear in mind we are not counting from 0 here, but from 1. If the cycle number corresponds to the pixel lit up in the sprite, then we are actually lighting up that particular pixel on the CRT. There's only one new test, which looks like this. We just give the output that we expect. To get the CRT output, we once again read the instruction and build the whole X registry throughout our cycles. During this part, I learned pretty quickly that probably the first value of the X register is not really important and I could have skipped it altogether. So I skipped the first value, and actually the very last 241 value is also useless, so I just skip it again. Then I split our cycles into 6 rows. And for each row, we just run getLine. getLine uses the value of the X register, but also the indices of that value. Now, what is getPixel? It's returning us either the lit up pixel or the blank pixel. First, we normalize the index. As I mentioned, the cycle index goes from 1 to 240, but our sprite index goes only from 1 to 40. We need to normalize that index to be able to compare those. This line, based on X registry, is actually building the whole sprite. If the pixel is contained within the sprite, we return the lit up pixel. If it's not, we return the blank pixel. Let's see again the CRT output. The CRT output is in here, and it's actually kind of hard to read with that font particularly, but you can read it if you focus. So it's R, G, L, R, B? Is it B? Yeah, it's B, Z, A, and U. You see that? Thank you very much, guys. I'm happy you guys have been here. I hope you like F#, because there's more coming in. Actually, the next day is starting to get really interesting. And as always, we can do better as a pack. Bye. And the input is just... what is it? Like, how do you call it actually? You gotta execute different lines. Not kill them, but execute what they want to do. And we build all the values throughout the every Last test covers reading the input and also observing the signal strength throughout. Come on! To cover available, we're and then we calculate get CRT output from the beginning, from the input from the beginning.